Now that we have some of the basics of thermodynamics under our belts, we will start looking into doing some thermodynamic analysis of systems. The easiest systems are closed systems, so that is where we will begin our little adventure. Remember that in a closed system, there is no mass flow in or out of the system, so the only way energy can be exchanged with its surroundings is through either heat or work. A very common form of work performed in a closed system is called PDV work. This is done by changing the volume of a gas, either through expansion or contraction. A common example of this is in a piston cylinder device, such as in your car's engine. This is also called moving boundary work. The boundary of the gas is changing as it is being compressed or expanded. We will start out with a simple scenario, that of a quasi-equilibrium process. This assumes that the process occurs slow enough for the entire gas to be in an equilibrium state throughout the whole process. These processes result in the maximum efficiency. We will see why this is the case later in this course. The amount of work done on the piston in these cases is given by delta W equals PdV. This comes from the definition of work, force F times displacement ds, in which the force can be replaced by pressure times area, then area times ds is dV. Note that the delta in front of the W indicates the path by which this process occurs has an influence on the actual amount of work done. Given this equation, it can be seen that if the volume of the gas increases, this leads to positive work, while compression of the gas leads to negative work. At this point, it is useful to remember the standard sign convention for work. Positive work is done by the gas, so expanding gas does work on some other object, such as a piston, yielding more energy in that second object and less energy in the gas itself. The amount of work done can usually be calculated by this integral down here. The work is equal to the integral from state 1 to state 2 of the pressure P times the change in volume dV. And again, be careful with minus signs and which way the energy is actually moving. If the pressure is constant, then this is simply P times the change in volume, delta V, or V2 minus V1. However, the pressure is usually a function of the volume. That is, if the volume changes, then generally so does the pressure P. So to evaluate the integral on the previous slide, we need to know this dependence. This is given by the process path. Graphically, this makes our lives a bit easier, as the integral becomes the area under the curve. So for instance, in this graph up here, representing the piston expansion process, the work done by the gas is the area under the curve up here. So it can be seen that the amount of work done will in fact depend on this process path curve. As an example down here, we can see 3 different process paths, each with a different amount of work being performed. So area under C is less than area under A, so A will do more work, as you can see. If we have a cyclic process, such as this last case over here to the right, then the system returns to initial state 1. If it returns along the same path, then no work is done. However, if we go from 2 to 1 along a different path, as seen down here, we can get some net positive work out of the system. This is what is hopefully happening in your car's engine. Otherwise, you're not going to go very far. There are a few common process paths that we will consider in this class. The first of which are called polytropic processes. This is any process where the pressure and volume are related through the equation P times V to the n power equals C, where n and C are constants. One example of this is Boyle's law, which is defined for a constant temperature process, in which case n equals 1, and we get pressure times volume equals constant. For any polytropic process, we rearrange the equation so that P equals C over V to the n power. We can then calculate the amount of work done by plugging this into the integral, yielding P2V2 minus P1V1 all over 1 minus n. This only works, however, if n is not equal to 1. If n is equal to 1, such as in Boyle's law or in the ideal gas law, then we get an integral of 1 over v, which becomes a natural log. So in this case, the amount of work done is given by P times V times natural log of V2 over V1. Note that in the case of an ideal gas, we can replace P times V in the equation on the previous slide to get this equation relative to a change in temperature for the work done in a polytropic process. Again, assuming n is not equal to 1. If n is equal to 1, then we can do a similar substitution as we did down here. So we have mRT in front of the natural log instead of p times v. The majority of thermodynamics analysis begins with application of the first law of thermodynamics. There are a few ways to implement this. One of the most popular is performing an energy balance. This is simply keeping track of any energy entering or leaving our system. Then using conservation of energy, the change in energy of our system, delta E, must be equal to the total energy coming in minus the total energy going out. Of course, this could also be done per unit mass or per unit time, depending on the question at hand. For a closed system, the energy coming in or out will be in the form of either heat or work. Remember, there is no mass flow across the boundaries in a closed system. So we can also look at the total work and heat going in and out of the system. In terms of these variables, total work and heat coming in minus total work and heat going out gives the total energy change of the system. For cyclic processes, the initial and final states are the same. This also means that the initial and final energies of the system are the same. So delta E in this case will be 0 for these systems. In this case, the total heat in must be equal to the total work out, or vice versa. And again, this should also be analyzed in terms of per unit mass or per unit time variables, or both. Here is the standard pre-lecture example for today's video and the answers. As usual, bring any questions you have to lecture.